In this video, I'm going to look at 3 different types of chemical reactions. The first one is synthesis, and what you'll notice is that there are 4 different subcategories within synthesis reactions, and these subcategories you are responsible for knowing, but with enough practice it'll come second nature. So the first type of synthesis reaction is when you form just a binary compound, and this is what we consider to be the traditional synthesis reaction, in which you have 2 different substances, A and B, and they come together to form one compound, AB. Alright? For the next one, you have a metal oxide and a non-metal oxide, and when those 2 come together, they form a salt. For the next one, when you have a metal oxide reacting with water, it's going to form a base, and we'll talk about what salts, base, and acid, what that means in just one second. So when you have a metal oxide and water, it's going to form a base. And the last one, when you have a non-metal oxide and water, it's going to form an acid. So what I'm going to do is I'm going to go over a couple of the terms that I just talked about, and then I will give you an example, and in class you'll get plenty of practice with these. Alright, so let's talk about some of these terms. First, acids. An acid is a chemical that begins with H, then it has a non-metal, and then sometimes it is followed by an oxygen. So for example, H2SO4, sulfuric acid, HNO3, HCl. However, there are some exceptions. For example, acetic acid does not begin with an H, instead the H is at the end. So just be careful, you'll become familiar with a lot of the acids. Most start with H, some do not. The next term that you looked at in the previous slide was the term bases. Now remember, a base ends in OH and it has a metal in front. Now of course there are exceptions. One common exception of a weak base is ammonia, which is NH3. And there are going to be other examples of weak bases that are exceptions, but that's the most common one. The next term that I used was metal oxide. A metal oxide is exactly what it sounds like. It is a compound that has metal and oxygen in it. So the metal goes first, followed by oxygen. So an example would be calcium oxide or sodium oxide, all of those examples that we've already looked at. A non-metal oxide is also a compound, but instead of being a metal and oxygen, it's a non-metal and oxygen. Okay? So for example, SO3. Notice metal oxides and non-metal oxides are binary compounds, meaning you have either the metal and the non-metal, followed by oxygen. You don't have any other atoms that are involved. Alright, the next term is salts. Now, a salt is a metal and a non-metal combined together. They are not bases, they are not oxides. However, their format, so meaning they're not oxides in the sense that you just have a metal and oxygen or a non-metal and oxygen. Instead, you have a metal followed by non-metal, and then you can also have oxygen at the end. So an example of a salt would either be copper sulfate would be an example. That's your metal followed by non-metal sulfur followed by oxygen. Other common salts are sodium chloride, which don't have the oxygen. Alright, so let's actually look at an example of a synthesis reaction. One key thing for you to remember are your diatomic elements that you learned in first year chemistry. Those diatomic elements are elements that in their atomic form they cannot exist by themselves because they are not stable, and as a result there are 2 of them bound together by a covalent bond. There are 7 of them. They make a 7 on the periodic table except for hydrogen, which is an outlier. They include oxygen, nitrogen, chlorine, bromine, iodine, hydrogen, oxygen, and fluorine. They make that 7 on the periodic table. If you don't remember that, ask me and I can quickly show it to you. So just keep in mind that whenever those atoms are by themselves, they're not actually by themselves, they exist as diatomic elements. There are 2 of them. So if we look at this first example of a synthesis reaction, it tells me that hydrogen gas is burned in air. Note, whenever I'm saying something is burning in air, we're not considering the other gases that are involved, we're simply considering oxygen. So what this is telling me is hydrogen is going to be reacting with oxygen. So hydrogen is diatomic, so it would be H2. It's going to react with oxygen, so plus oxygen, which is O2. And let's figure out what that's going to produce. If you have hydrogen and oxygen, okay, that's going to be the first type of synthesis reaction that you looked at, in which you have A plus B producing AB. And so the compound that's going to be formed is H2O. Keep in mind, if you have a metal and a non-metal combining together to make a compound, you're going to need to cross your charges in order to create the compound with a neutral charge. So that is a synthesis reaction. You get lots of practice with all the other types of synthesis reactions in class. Actually, notice that I'm not quite done. I have 2 hydrogens on the left-hand side and 2 on the right, so I'm balanced in that sense, and I am following the law of conservation of matter. But notice I have 2 oxygens on the left, but only 1 on the right, which means I need to put a 2 in front of H2O. And now, since I have 4 hydrogens, I need to put a 2 in front of H2. The next type of reaction that we're going to look at are decomposition reactions. Notice there are more subcategories of decomposition reactions, but again, you'll get plenty of practice with these. The first couple are actually, you'll notice some are just the reverse of synthesis reactions. They're just the opposite reactions. So for example, the first one, for a binary compound, if you have AB, a compound AB, it's going to break apart into A plus B. That's the exact opposite of what we looked at with synthesis reactions. If you have a metallic carbonate, so MCO3, it could be sodium carbonate, it could be magnesium carbonate, it's going to break apart into a metal oxide and carbon dioxide. Similarly, if you have a metallic hydrogen carbonate, it's going to break apart into your metal oxide and carbon dioxide, but notice you also have water as one of your products. For a metal hydroxide, remember a metal hydroxide is a base, and so this is actually just the reverse of what we already looked at with synthesis reactions. You're going to have a metal oxide and water forming. For a metallic chlorate, it's going to break apart into a metal chloride and oxygen. For an acid, notice this is the exact opposite of your synthesis reaction, which you have a non-metal oxide and water. So an acid's going to break apart into water and your non-metal oxide. Finally, similarly, you had a metal oxide and a non-metal oxide that form a salt in a synthesis reaction. The exact opposite happens in decomposition. If you have a salt with a metal, a non-metal, and oxygen, it's going to break apart into a metal oxide and a non-metal oxide. Notice that while synthesis reactions, you have 2 different components that are coming together, 2 different substances that come together to form one product. In decomposition reactions, you have one reactant that breaks apart into 2 or 3 different substances. So let's look at an example. Calcium hydroxide is decomposed. So the first thing that I need to do is write the formula for calcium hydroxide. The formula for calcium hydroxide, since calcium has a +2 charge and hydroxide has a -1 charge, is CaOH2. Now that's going to decompose, so I need my arrow, into, well, think about what type of decomposition reaction this is. You have a metal and hydroxide, and so your products are going to be a metal oxide and water. Now, your metal in this case is calcium, oxygen is O, so when you cross your charges, it's just going to be CaO, and your other product is going to be water. Now I need to check my balancing. Keep in mind I have 1 Ca on the left-hand side, 1 calcium on the right. I have 2 oxygens on the left, I have 2 on the right, and I have 2 hydrogens on the left and 2 on the right, so I'm actually already balanced. The last type of reaction that we're going to look at are combustion reactions. Now, combustion reactions are all extremely similar, almost identical, except for the hydrocarbon that's involved, and I'll talk a little bit about hydrocarbons in just 1 second. The general format for a combustion reaction is a hydrocarbon reacts with oxygen and it produces carbon dioxide and water. So let's talk about what exactly a hydrocarbon is. A hydrocarbon is a compound that has hydrogen and carbon. Now, the most basic hydrocarbons that we'll look at are called alkanes. Notice I'm very briefly going to be talking about a little bit of organic chemistry. We're going to get much more into detail with this second semester, but just as an introduction, alkanes are hydrocarbons, so compounds that have hydrogen and carbon, and they only have single bonds. So if you look at this table below, start to get familiar with some of these names. So for example, CH4 is methane. If you have C2H6, so you add a carbon and you add 2 hydrogens, you have ethane. If you have 3 carbons, propane, 4 carbons, butane. After that point, notice all of the prefixes are similar to those that we used for naming molecular compounds. So the first 4 are the only ones that you really need to memorize, because after that point, pentane would be 5 carbons, hexane would be 6, heptane 7, octane 8, nonane 9, and decane 10. Notice for the number of hydrogens, this is just to get you guys a little bit comfortable with organic chemistry. The number of hydrogens is the number of carbons times 2 plus 2. So for example, for methane, you have 1 carbon, so that would be times 2, so you got 2 plus 2, so a total of 4 hydrogens. For ethane, you have 2 carbons, so times 2 would be 4, plus 2 would be 6. For propane, 3 carbons times 2 plus 2 will give you 8, etc., etc. Now we'll look at the actual structure of these to understand why exactly there are 8 hydrogens. You accomplish that by using Lewis structures, but for the moment, just keeping in mind that methane is CH4, ethane C2H6, keeping in mind that pattern for figuring out hydrogens, just in case in a problem you're asked to write the formula for one of these alkanes. Now, the other concept I wanted to go over are organic alcohols. Organic alcohols are hydrocarbons. However, they have removed one of the hydrogens and added OH to it. So a great example would be methanol. So it's methane, CH4, it removed one of the hydrogens and added OH to the end. So the formula for it is CH3OH. In this example, ethane is burning in air. So this is going to be a combustion reaction because ethane is a hydrocarbon and air would be oxygen. So the formula for ethane, keep in mind, is C2H6, and it's going to react with oxygen, and the products of combustion will always be carbon dioxide and water. So the only other thing that I have left to do is to balance my reaction. I have 2 carbons here, 1 carbon here, so I need to put a 2 in front here. I have 6 hydrogens here, so I need to put a 3 here. And then I have to figure out my oxygens. I have 4 oxygens here, I have 3 oxygens here, so that's a total of 7. So what I can put in front of O2 is 7 over 2, because that gives me 7 oxygens. Now I can't leave it like that. I can't leave a decimal for a coefficient. And so what I need to do is I need to multiply this entire reaction, all of the coefficients, by 2, and it will stay balanced. So this is going to be a 2 here, this is going to be a 7, this is going to be a 4, and this is going to be a 6. One other type of combustion reaction that you might see in addition to the simple hydrocarbon and oxygen reaction is a metal sulfide and oxygen. So if you have a metal sulfide and it reacts with oxygen, rather than producing water and carbon dioxide, what it produces is a metal oxide and sulfur dioxide. So this is one of the funky exceptions. To help you remember a hydrocarbon has hydrogen followed by carbon and oxygen. So keep in mind that the metal and the oxygen combined together would be the equivalent of water, and then SO2 would be the equivalent of your carbon dioxide. So as a quick example, if I had copper sulfide and it reacted with oxygen, what it would produce would be copper oxide. Well, copper in this case has a 2+ charge, so it would be copper oxide plus sulfur dioxide. And so the only other thing I have to do now is I have to balance my reaction. I have 2 oxygens here, I have 3 on this side. And so what I'm going to do is I'm going to put a 2 in front of copper oxide. That gives me 4 oxygens. So I'm going to put a 2 here. That gives me 2 coppers here. Unfortunately, I now have 2 sulfurs while I only had 1 here, so I need to put a 2 here, which messes up my oxygens. I have 2 oxygens, 4 oxygens, so a total of 6, so this needs to become a 3. So that's just one of the exceptions for combustion reactions. You're going to have lots of exceptions, but just keep that one in mind.